that the x's are non-stochastic. We said that the vector u is a random vector. So therefore, what's the implication for the way in which we use the expectation operator, big E? Since these two terms multiplied just give us the identity matrix, and beta is a constant, the expected value of constant is just a constant. So I'm thinking about x prime x inverse x prime u. What's that expectation? And because does the expectation operator have to operate on x times u or just the u? Because right. And we already know that the expected value of a linear combination of random variables is the linear combination of the expectation. So because the expectation operator is a linear operator, and because u and x are independent in a statistical sense, the expectation operator just marches right past all the x's and operates on the random vector u. And by assumption, the random vector u has what mean?
And u has a mean of 0, right?
Yes. We told that was a garden variety assumption. So I can write that as x transpose x. This is what I was going on with G about. And by assumption, the expected value of u is 0. So my estimator is unbiased. So we also said we wanted to say something about efficiency. So if we're going to say something about efficiency, we have to know about the variance of beta hat. How am I going to figure out the variance of beta hat? Yes. But I want to derive, before I can discuss that, we've already decided that beta hat is linear and it's unbiased. Now I have to figure out its variance. And then I have to go one step further than that and compare its variance to every other possible linear estimate that's unbiased. So tell me how to derive the variance of beta hat. What's the definition of the variance of any random variable? Suppose you have a random variable v. How do we using expectations, how do we figure out the variance of v?
Is the expectation and v minus the expectation of v.
Right. So now we got to do that for that. So get us going. Tell me what to write. I want to know the variance of beta hat.
Also the expectation of beta hat minus e beta hat. And
Close forever?
yeah. And times another beta hat minus.
Are those two vectors?
Yeah, actually they're the same thing. Which I can transpose.
This is n by k, right? And this is n by k. Can we multiply those two vectors, those two matrices?
I need to transpose.
The first one I need to transpose.
Yeah.
Because I want the covariance matrix for beta hat. Since there's only k of them, there can only be k times k minus 1 over 2 covariances, right? So I need to transpose. There are k unknowns. Beta hat is a random vector. There are k of them. So its covariance matrix must be k by k. Yeah, there are typos. So Zen, what's the next step? How about if we do what GU was trying to get us to do before? We told us substitute away from some things. Now we already discovered by pounding away on somebody else that beta hat minus beta was equal to that, right? Didn't we discover that already? So let's substitute away from that difference. It's just going to be x transpose x inverse x transpose y transpose x transpose x inverse x transpose y. We would like to state our variance of beta hat in terms of the random vector u. Isn't beta hat equal to x transpose x inverse x transpose y?
Yeah, so then what happens to it?
Oh, I'm sorry, right. Minus, right. I'm trying to do two different things. had that the expected value of beta hat was equal to beta plus x transpose x inverse x transpose u, right? Didn't we have that a minute ago? Let's subtract beta from both sides, so that now we have the expected value of beta hat minus beta is equal to x transpose x inverse x transpose u, right?
Just the expectation of you, not. Isn't that the expectation of you rather than time?
We had that beta hat is equal to x transpose x inverse x transpose y. And then we wrote that beta hat was equal to x transpose x inverse x transpose x beta plus u. We then had that beta hat is equal to x transpose x inverse x transpose x beta plus x transpose x inverse x transpose u, right? So that beta hat minus beta is equal to x transpose x inverse x transpose u. Okay?
That first row, is that Y or is that U? Yes.
That's a y, and I substituted away from y, and then I just did a little rearranging of terms.
And that is just supposed to be that, not the expectation. Of what you wrote just now, over there.
This.
What you wrote
Suppose I
earlier.
took the expectation, I already know that the expected value of beta hat is equal to beta. So this is the same as that, right? Because this is just beta. So we're still at the point where we're saying the variance of beta hat is equal to that expectation. So when I take the transpose of the first set of parentheses, I end up with u prime, expected value of u prime, x, x prime, x inverse. What's going on here? This is k by 1, and I want the transpose out there, 1 by k. There we go. Everybody see the atom state up here?
What is slide was correct?
Yeah, I guess so. Okay. So it should be beta hat minus the expected value of beta hat, first multiplied by the transpose of the same thing. So I had to put a transpose here, I moved it out here. So I get the expected value of x prime x inverse x prime u transpose x times x prime x inverse. And the same argument that we used before, the expectation operator is a linear operator. The x's are non-stochastic, so we can go right through and we can operate on sigma squared, the expected value of u transpose. And we already know that the expected value of u transpose, that was equal to what? The expected value of u transpose was equal to what?
Expected value of the transpose is equal to x squared minus.
Sigma squared I. Right. Remember, we're reserving the Greek letters for parameters and the Roman letters for samples.
Yeah. For the expectation of beta hat minus expectation of beta hat, like matrix there, it's k by 1 times 1 by k. So it will be a matrix of dimension k by k, right?
Right.
What's the expected value of the matrix with the dimension k by k? It's also matrix?
So it's equal to
Or is it-
sigma squared, it's a scalar, times x prime x inverse. And we said that the x's were non-stochastic, so we're done with the expectation operator. Well, when I take expectations, you just told me the expected value of u transpose was sigma squared times the identity matrix, right? So let's do that. Sigma squared is a scalar, correct?
Yeah. Take that out.
Take that out. So I have x transpose x inverse times x transpose x